Okay, last week, wrapping up lecture, we're talking about electrical insulators, we're talking about conductors, things of this nature, right? I dug out of my archives here. Remember I talked to you about mica? Mica? I found my stash, my private stash of mica. Please be very careful passing this around. It actually kind of flakes off, so you can just handle it, look at it. This is found in nature, it's found in rock formations, and this is the best insulator found in nature. This is a washer, an insulator washer that's been made out of mica. Okay, so we'll pass these things around so you can see, but these are very fragile. Don't try to bend it, you'll break it. It's almost like a real thin piece of glass, if you will. So this is mica in the raw, and this is a processed piece that could be used as an electrical insulator. So cool stuff. So anybody have any questions on anything else before we get started here? Chapter number 2. Okay, just to get us kind of ramped up from where we left off last week, we really started our discussions last week talking about the fundamental properties of electricity, and that discussion really started off with a discussion about matter. Matter is everything. If there is no matter, the absence of matter is called space. We could recreate the absence of matter here on planet Earth by using an industrial vacuum chamber. That's where we pump all the gases out of the chamber and we're left with nothing inside. Industrial vacuum is used a lot in industry, in the manufacturing process, so that they can remove everything from it and only introduce those materials that they want to be inside the chamber. Remember that discussion? Okay. The next thing we talked about, which is very, very critical, are the properties, the fundamental physics properties, if you will, of materials that are used in electrical and electronics applications. The most popular that we talked about is the conductor. The conductor is a material that has 3 or fewer valence electrons in the valence shell. Okay? That means there's basically, we talked about it like a parking garage. There's room for electrons to park in this valence shell. Therefore, it's going to make it a good conductor. Materials that have 5 or more electrons in the valence shell are good insulators, like that piece of mica that we're passing around right now. If you looked at that, you'd see, again, more than 5 electrons in the valence shell. That means if you're a free electron, you're not going to have any place to park on that piece of mica. We also talked about semiconductor materials. Those are materials that have 4 electrons in the valence shell. And for those of you that continue on in this program, ELEC 120, that's right where we're going to pick up the discussion, back to fundamental properties of physics as it pertains to materials. If any of you were in the classroom the other night, last week, I gave that lecture to ELEC 120, and we were talking about these fundamental properties, subatomic structure, because that discussion was all about solid state materials, silicon, germanium, that we use in the manufacturing of transistors and integrated circuits. The other big thing we talked about is, in essence, the beginning, the creation of electricity. When we have matter and we impart energy on matter, we could knock an electron off that valence shell. When we knock an electron off that valence shell, we end up with what's known as a positive ion. A positive ion. Because remember, in nature, matter is typically in a neutral state. That means it has an equal number of protons and an equal number of electrons. Remember that? That's how we end up with the atomic weight. Atomic weight or atomic number? Number. Which one is it? A is weight, B is number on the quiz. C is both. D is none of the above. Which one's it going to be? The number of protons is number. Okay? So that number, whatever number of protons we also have the same number of electrons. That's what puts it in a neutral natural state. So when I impart energy on matter and I knock an electron off, now I have more protons that have a positive charge than I have electrons in the atom. That makes it a positive ion. In essence, what I just did is created electricity. That's what electricity is. Electricity is us applying energy to matter, knocking an electron off, gathering those electrons, and then saying, hey, electrons, have I got a deal for you? You want to get back to your parent atom and get it into a neutral natural state? Come this way. Go through this circuit. Do a little bit of work for me, and then I'll give you a path back to neutrality. And the electrons, they do this. So part of your careers in the electronics industry is going to be simply managing the behavior of electrons, making sure the electrons do what they're supposed to do. I guess that's why they call this electronics, right? Electronics, the study of the behavior of the electron. That's what this is all about. The other thing we talked about last week briefly was the coulomb, a unit of measure, right? A coulomb is like a gallon of gas, a dozen eggs, a bushel of apples. A coulomb is 6.24 times 10 to the 18th electrons. It's a big, huge Herkin number, right, of electrons. There was a guy by the name of Charles de Coulomb. He was counting electrons for a living, and then he died, you know? And then they said, hey, anybody here want to continue on Chuck's work? Anyone? Anyone? All right, we'll just call it even. We'll call, the number that he came up with, 6.24 times 10 to the 18th, we'll call that a coulomb. 1 coulomb per second is the ampere. That was put together by a guy by the name of Charles Ampere? No, Andre Ampere, another Frenchman, or Beret. Andre Marie Ampere. And you know what? Universally, that's accepted. See, the amazing thing, I enjoy travel all around the world. People speak different languages. We use different coins, different monetary values. When it comes to current, worldwide, the ampere is the accepted value that we use, no matter where you go. So, those of you that are learning, or if you have English as a second language and you struggle with this, we're all learning a new language. It's the language of electronics. And the word we're going to study tonight is current. Current. And you already know kind of a little bit about current based on our lecture last week. Well, we're going to pull back the curtains and study a little bit more tonight. After completing this chapter, you're going to be able to state 2 laws of electrostatic charges. I'm going to give you a heads up. Anytime you see the word law, you should sit up straight and take note. Because if it's a law, the type of laws we're talking about here are not laws that we could go to Olympia and have repealed. Okay? They're not talking about laws that we could go to the Supreme Court and have overturned. That actually would be kind of fun, wouldn't it? Go to Washington, D.C. Students from Lake Washington Technical College in Kirkland, Washington protested today outside the Capitol to have the laws of physics repealed. We can't. These are laws of physics, okay? So these electrostatic charge laws are kind of critical. We're going to be able to define coulomb, identify the unit used to measure current flow, define the relationship of amps, coulombs, and time through formula. Describe how current flows in a circuit. Describe how electrons travel in a conductor. Define and use scientific notation. And identify commonly used prefixes for powers of 10. Some of you may be familiar with this law. You've probably heard it before. The first law of electrostatic charges are like charges repel each other. Have all of you heard that one before? Okay. The other thing that you're probably familiar with is opposites attract, right? Opposites attract, and that's not only in relationships, that's actually the laws of electrostatic charges. Opposites attract is actually the second law of electrostatic charges. So if I got a negative and a negative, They're going to oppose each other. If I have a positive and a positive, they're going to oppose each other. If I got a negative and a positive, pow, they're going to be attracted to each other.
Same concept with magnets?
Yep, very similar. That's not electrostatic, that's magnetism. It's a different property, but the same thing. North is going to be attracted to south. You got two north poles, they're not going to be attracted. They're actually going to push back on each other. Two south poles, the same thing. So we're actually going to study that in future chapters. But this is the law of electrostatic, not electromagnetic. So just keep those two separate. Coulomb. Coulomb is the unit adopted for measuring charges. In last week in lecture, I gave you the number 6.24 times 10 to the 18th. I figure I'd wait a week before I actually showed you what that number looks like. I mean, it's one thing for me to say up on the board it's 6.24 and then 16 zeros after, but this is really what the number looks like. Okay? It's really what the number looks like. One of the reasons that we need to use this form of notation is that this number right here will not fit in your calculator. It won't fit in your calculator unless you enter it in this form. And I'll show you. By the end of the lecture, I'll show you how to make sure you know how to enter it in that form. It's kind of funny because if you had your neighbor down the street or whatever, and you found out that they were going to college in an accounting program, right? If they're going to go to school to become an accountant, you'd probably say, wow, that person must be really good with numbers, okay? Tell you what, if you're Bill Gates' accountant, you're not dealing with a number like this, okay? But yet, regularly, on a daily basis in the study of electronics, we're going to be dealing with numbers like this. So, if you're struggling with this form of notation, we'll work with you. But don't be like me. When I was in school initially like this, I looked at this number and I looked at this stuff and, man, I don't know, that's too complex. It's like, 6.24 times 10 to the 18th, that's a number like Mr. Spock would use or something on a Starship Enterprise. And I'm a more down-to-earth guy, so I'm going to keep it basic, And in very short order, I realized you can't keep it basic in electronics because we're going to be dealing with these extreme numbers. So we have to use this form of notation. So you see how we came up with this 6.24 times 10 to the 18th? The decimal point here means there's 18 places past it. So if we went ahead and actually counted here, right, that's like us moving the decimal place from here all the way up to here. So if we went ahead and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 6.24 times 10 to the 18th. That means there's 18 places past the decimal point. In this particular case, since I have 0.24, that means there's going to be 16 zeros after it, right? 16, 17, 18. 16 zeros after that. Does that make sense? Everybody see how I did that? All right. There's our first law of electrostatic charges, negative and a negative, positive and a positive, negative and a positive, Because remember, in the beginning, everything was in a neutral natural state anyway, right? So originally, everything was like harmonious, balanced. When we apply energy to matter, we knock an electron off that valence shell. And all is that valence shell, that electron that we knocked off has in mind is getting back and putting that atom in a neutral natural state. So if you put an electron in the same room with a positive ion, they're going to seek each other out. They want to achieve balance and harmony. Make sense? Current. And every time I use this word here, we should like ring bells, chimes, hit a gong, something like that, because this is like a holy word in electronics. There's 4 properties that you really need to be infatuated with. And when I say infatuated with, I'm not talking about just as a student. I'm talking about later on when you continue on with your career. The worst day you have in this industry as a paid electronics professional, the problem will be solved by understanding and knowing the behavior of voltage, current, resistance, and power, period. Do I sound like I'm oversimplifying it? I'm not. It gets that basic. If they've got an electrical problem with the space shuttle and they can't hit the button and have it blast off, it's because voltage, current, resistance, or power isn't doing what it's supposed to be doing. So if you know everything about those 4 parameters on the space shuttle, you could get in and look at those 4 parameters and quickly find where the problem is. So today we're talking about current. We should ring bells, hit chimes, hit a gong or something, because current is one of the big 4 properties. Now the textbook talks about current as being the drift of electrons from an area of negative charge to an area of positive charge. I don't like this definition, the drift of electrons. Makes it look like I'm an electron and I'm drifting, I'm floating, okay? An electron is more like if I'm negative charge and there's like positive ions out in the freaking hall, I'm gonna be like, I'm going to be trying to get over there. Why? Because I want to fill those holes. I want to fill the void that was created when energy was imparted on matter. Does that make sense? So that's really the behavior of current. As a matter of fact, that was kind of a mad dash. I bet you didn't think I had it in me, huh? It gets better than that. You know how quickly electrons are going to go over there if you could complete the path? At the speed of light. At the speed of light. If we allow electrons to complete the path, it's going to travel at the speed of light. So I don't call that the drift of electrons, negative to positive. Now, Andre Marie Ampere came up with this term that he called the ampere, named it after himself. These dudes didn't have egos. You kidding? They didn't have egos. Andre Marie Ampere invented a unit of measure called the Smith. No, the ampere. The ampere is the amount of current in a conductor when 1 coulomb of charge moves past a point in 1 second. This is kind of emotional. This is your first real formula. It's your first real formula. The relationship between amperes and coulombs per second can be expressed as I, which is current, is equal to Q, charge measured in coulombs, divided by T, time measured in seconds. So what we're saying here is 1 amp or ampere is equal to 1 coulomb per second. Now be careful with this, because I could ask you a question about number of electrons. Is number of electrons coulombs? Number of electrons is number of electrons. Coulomb is 6.24 times 10 to the 18th electrons. So this formula only works if you're using coulombs. What happens if I have half a coulomb per second? It's not a trick question. If I have half a coulomb per second, what's my current going to be? Half an amp. If I have quarter a coulomb per second, what's it going to be? Quarter of an amp. If I have 2 coulombs per second, this is a trick question. No, just kidding. 2 coulombs per second. That means I'm going to have 2 amps. So typically for household current in your home, we talked about this last week. What was that number? What's your typical utility connection from the power company to your home? That's the voltage. What's a typical box?
200 to 250.
Typically about 200 amps is a typical residential connection. You know, you buy a home, you're going to see that it's typically 200 amp connection from the power pole, or if you have underground service, to your box, that big gray box that's in your house, 200 amps. Okay? From that box, the circuits in your home get distributed to circuits that are typically either 15 amps or in some cases 20 amps. And for some of your appliances, you know, they'll be a little bit higher in some cases if you have an electric hot water heater or things like that. I've got a hot tub, okay, it requires more than 15 amps, more than 20 amps, so I've got a high current connection going to that. So if you've got 15 amp outlet in your home, that means that outlet is capable of handling how many coulombs? per second? 15. 15. I could also ask you how many electrons per second can that handle? Then you'd have to get 6.24 times 10 to the 18th times 15, and that's how many electrons it would be physically that's capable of supporting. That's why it's so critical that all of these components, when they're manufactured and they're given their specifications, that you don't exceed those specifications. Because if you try fitting more electrons through than it's physically capable of handling, you're going to start an electrical fire. Okay, so everything has ratings associated with it, current ratings, and this is why. Physically, it can't handle any more electrons. If you try pumping, if you got a garden hose and connected it to a fire engine, okay, and turn the pumps on high, what do you think is going to happen to that garden hose? It's probably going to blow up. It's probably going to explode, right? It can't handle that volume. That's why firemen have like big hoses, okay? Because they have a higher volume of water that they try to put, from the truck onto the fire. That's why they're firefighters, fire people. Make sense? The other thing I want to share with you about formulas, okay? If there's shortcuts that I could teach you and you could remember, I'm all about that. This is college, so whenever I give you a formula, I'm just going to give you this formula and assume that all of you are like college students that have paid your dues and are here for the right reasons. So I'm not going to show you every possible variation of the formula. I'm going to expect you to know how to do it on your own. But I don't expect you to know how to do it on your own because all of you don't have a comprehensive algebra background yet. So I'm going to show you a couple shortcuts here, a way to cheat. What I want you to do is start off with drawing a triangle. I want you to draw a simple triangle. Then inside the triangle, I want you to draw a T. The one formula that you know, I want you to plug into this triangle. So I, in this particular case, I is equal to Q over T. Does everybody see how I did that? I is equal to Q divided by T. So that's the first formula that I gave you. I is equal to Q over T. Now on a quiz or an exam, or simply when you're hanging out together working with each other in the lab, what happens if I gave you coulombs and I gave you current? Then what we could do is simply cover up the letter T and say T is equal to Q over I. So I did that? So T is equal to Q over I. That's the other algebraic manipulation of this. If I asked you on a quiz, if I gave you current and I gave you time, and I wanted you to figure out how many coulombs, what the value of coulombs would be, then we simply cover up the Q, and then it's going to be I times T. See, the I is next to the T, so it's going to be I times T. So that's going to be our other variation. Q is equal to I times T. So with that one formula that I gave you, there's three basic algebraic manipulations that we could have, and this is all of them. So do you have to memorize these? No. Remember, do the triangle, put the T in the center, and then lay that one formula out. And then now you have all the algebraic variations of that formula. And you know what? You need to know how to do this, because I could ask you, I'll be honest with you, everything right now is fair game. I could ask you to solve for current. You should be able to do it. I could ask you to solve for time. You should be able to do it. I should ask you to be able to solve for coulombs, and you should be able to do it. I should be able to give you a number of electrons, right? You have 30 gazillion electrons. How many coulombs is that? That gives you this value. Then you could figure out the rest. Does that make sense? So it's a stepping stone. But don't get hung up on what you don't know. Focus always on what you do know. And the one thing to remember is 1 amp is 1 coulomb per second. I is equal to Q over T. And then if lay that out, gives you all the other variations. Make sense? Is that right? Hole. An all-female progressive rock band from Seattle, Washington. Hole. That was a joke. Is Hole even still around? No? No? No. They're not. When did they disband? Where did they go? No. She's doing her own thing. Yeah, that's what I understand. She's doing her own thing. So reference, what Beavis and Butthead Do America, right? There's a reference to Hole. Not this Hole, but the other Hole. Remember they were, no, seriously. They were going, remember Beavis and Butthead Do America? They're looking for their TV, or the TV broke and they stole one and whatever they're doing. But they were going to go to Washington, like D.C., but when they heard about Washington, they were like, Washington, that's cool. It's like where Seattle is. We could go see Hole, So anyway, that's required viewing for all of you. Beavis and Butthead Do America. It's going to help you understand. Anyway, no, I'm talking about a different type of hole. Hole that I'm talking about here is the absence of an electron. If I have an atom, and I apply energy to matter, and I knock that electron loose, what do I leave behind? A hole. So a hole is nothing more than the absence of an electron. The reason I want to point this out to you is that here at Lake Washington Technical College, every other technical and community college in Washington State, in the country, the U.S. military, all branches of the U.S. military, technical schools, a lot of universities all embrace what we embrace, and that is electron flow. We call 1 amp 6.24 times 10 to the 18th electrons traveling per second. That's what we call 1 amp, right? Engineers, scientists embrace what's called hole flow. They think that the holes are flowing to get filled by the electrons. I don't want any of you to lose sleep over this. Whether 6.24 times 10 to the 18th electrons travel in that direction per second, that's an amp, or it's 6.24 times 10 to the 18th holes that travel in that direction per second, that's going to be an amp. But hole is the absence of the electron. And the reason I'm pointing this out to you is I know all of you this weekend, as soon as you get a little bit of time off, you're probably going to go to the library and pick up some electronic books, start reading. I don't want you to call me a liar. I don't want you to open up that book and say, hold on. This book shows that current flows positive to negative. That Joe Grenick over there at that Lake Wash, he doesn't know what he's talking about. He said that current flows negative to positive. Current does flow negative to positive. Electron flow. Current also flows positive to negative. Hole flow. Are any of you going to go home and lose sleep over this? Be honest with me. Okay, let me know, because I did. I honestly, when I was in school, I got the same lecture I'm giving you right now, and I'm like, oh, no, I didn't raise my hand. But then I went home, and I'm like scratching head. What the heck was he talking about? You know? And I for months, I freaking tried to analyze. It's not that difficult of a concept. You just got to hit the I believe button. Joe says 6.24 times 10 to the 18th electrons per second equals 1 amp. So be it. We do want to talk about hole briefly so you can differentiate between electron flow and hole flow, and also to prepare you for what you are about to receive in the future. Because again, if you sat in on my lecture last week on ELEC 120, guess what? We started talking about hole flow again, because hole flow is significant in the study of semiconductor devices, solid-state devices. If you want to understand how a transistor really works, you have to embrace hole flow. So we are going to talk about it more here at Lake Washington, but you don't need to beat yourself to death on it. Question?
Do holes have matter in them?
Well, you got to realize that the hole itself, no, is the absence. But if you're talking about matter that exists and it's the absence of the electron, then we're really talking about a positive ion. And a positive ion does have mass because you got all your protons, you got all your neutrons, and of course that's how we determine atomic weight. Very good. Answer A. Fill in the A. Atomic weight, number of protons and neutrons. So hole is the movement of an electron from one atom to the next, creating the appearance of a positive charge moving in the opposite direction. So that's what we call hole flow. If you had a piece of copper, which we know copper is a good, abundant conductor, this is kind of how the electron path, how it would work. Negative to positive, kind of copper atom, it would jump over here to copper atom, jump over here to copper atom. Make sense?
Drifting along.
Drifting along at the speed of light. This here we see, again, a conductor. We've got electron flow left to right, current flow left to right, hole flow right to left. Make sense? Okay. I want to show you something how this really works, because the way they're making this look, and I think you guys are all buying this, right? Because again, you kind of got to believe me, right? But this is kind of like, the free electron is kind of like hopping from copper atom to copper atom, because there's 3 or fewer electrons in a valence shell, right? It's kind of hopping along, there's another copper atom, you know? You ever jump across a stream, right? It's kind of what they make it look like here, right? Okay. Everybody at this table here, can you just back up here? Nobody has a coffee or anything on here, okay? Can you put your hand on the end of the table just like this, okay? Okay, let me know how quickly you feel this. That is how current flows through a conductor. That's how current flows through a conductor. The speed of light, instantaneous. Instantaneous. If I've got a negative here and I've got a positive there, pow, instantly that is going to be felt on the other side. That's how current flows through a conductor. So it's not this. Got to have your tongue out when you're doing it too, right? Doesn't work like that. It's instantaneous. The speed of light, which is important. 186,000 miles per second. The speed of light is 186,000 miles per second. Or for those of you in the metric system, 300 million meters per second. 300 million meters per second. Or for those of you that keep track of all things nautical, 161,000 nautical miles per second. And I got a couple chuckles out there. It's kind of like, well, Joe's ex-Navy, he would probably know that. No. I'll tell you what, if you know those 3 numbers, 186,000 miles per second, 300 million meters per second, 161,000 nautical miles per second, if you know those 3 numbers, you could probably get about 8 or 9 questions right on your FCC license exam. Because it's how RF energy transmits as well. If you're working on a radar, you want to get your radar endorsement to be able to work on a radar. The only radar in the world that I am familiar with that operates in statute miles is the radar that's operated by the police. If you're on a Washington State ferry and they're looking at a radar, that radar is calibrated for nautical miles. So all the math that takes place internal is 161,000 nautical miles per second. If you go to work for the Federal Aviation Administration and you work at Seattle TRACON that keeps track of all the aircraft arriving to Seattle and departing Seattle, the radar that they're looking at is calibrated in nautical miles. And the aircraft also travel speed-wise in knots. In knots, which is nautical miles calibration standard. Okay? So that's why those numbers are very important. That's how fast current travels. That's how fast radio frequency energy travels at the speed of light, or close to the speed of light. There's actually some atmospheric anomalies that kind of slow it up a little bit, but generally speaking, it's the speed of light, which is also important to realize. That's why it's so great you got me as an instructor, because you could learn from all of my goofy mistakes. Back when I was in the Navy, the only way that I could get a raise, the only way that I could increase rank, was obviously not getting in trouble for a period of time, which is actually another funny story. I'll share that one with you in a second. I forgot all about it. But anyway, the other thing is by taking professional examinations twice a year. And I remember one of the exams, you would have thought I would have been ramped up with this stuff. I got to this whole section of the exam once when I was trying to, go up in rank. And they started talking about the behavior of antennas in outer space. And I was like, I'm a submarine guy. I have no freaking clue how this antenna is going to behave in outer space. What the heck are they talking about? The Navy's got like people in outer space, and I just got myself into a tailspin, and I couldn't even answer anything instead of looking at the obvious. How do antennas behave in outer space? Perfectly. Theoretically, perfectly. That's what they were looking at. So I got all those questions wrong because I could just, man, they're talking about going to freaking outer space. I'm not going to outer space. I want to live beneath the sea. So, more on that, on keeping out of trouble. Can't make this stuff up. I was looking at a copy of my medical record. I have a copy of my military medical record at home, and I was looking through it. And I came upon a page. I got into a slight altercation. And actually, the medical record reveals 25-year-old Caucasian reported to sick call, reports being worked over by 2 bouncers. And then it goes into how I slept well and I woke up somewhat sore. And basically, I reported the sick call, and it was I had my cheekbone got broken. And one eye was pointing one way and the other eye was pointing the other way. And finally they said, you got to go get that looked at. So, but right in there in print, reports being worked over by 2 bouncers. Called my son over. I said, check this out. It's kind of cool. I should have that framed, put that in my office, my medical record, But anyway, I was a good sailor. Voltage source. And again, we should almost ring bells, chimes, hit gongs when we're talking about voltage source. And I hope you don't think that I'm over-exaggerating this. These first few chapters of what we're talking about are the fundamentals. You have to understand this stuff 100%. Now, you need at least a 70% to pass this class. If I were truly the Pope of electronics, I'd say no. You don't move on to the next module, the next chapter, until you prove 100%, because this is how critical this information is. Voltage source, what we're talking about here is a power supply. It supplies electrons from one end of the conductor, and it removes electrons from the other end of the conductor. It can be thought of, for those of you that like using analogies, fluid systems, it could be like a pump. What does a pump do? It sucks from one end, it pushes out from the other end, right? This is what a voltage source does. It basically supplies electrons from one end and then sucks them back from the other end. That has to be taking place or it's not a valid voltage source. So a battery is a voltage source. We're going to talk more about batteries in future chapters, right? It provides electrons on the negative end of the battery, and it collects those electrons on the positive end of the battery. That's what makes it a battery. That's what makes it a voltage source. And we need a viable voltage source in order for us to have a viable circuit. Now finally, we're going to talk about scientific notation, but we're not. Actually, what I want to talk to all of you about tonight is what's known as engineering notation. Anybody here really comfortable using scientific notation? If you're really comfortable using scientific notation, I guess you could keep using it, but I would encourage you instead to use engineering notation. The difference is scientific notation can be times 10 to the first power, second, third, fourth, fifth, sixth, seventh, it could be anything. You follow what I'm saying? Can you dig it? Engineering notation is always going to be in groups of 3. It's always going to be in groups of 3, which lends itself very well to what we're doing here in electronics. Let me show you. Let's start off with a decimal point. Oops, there it is. There's the decimal point. Okay? So if I put something to the left of the decimal point, this is going to be my base 10. This is going to be my ones column. So this number here could be anywhere from 0 to 9. If I get 9 and I add 1 to it, 9 plus 1 equals 10. So I've got to go to my tens column. So this is my tens column, this is my ones column. Can you dig it? This is the part that I did well in school too, the number line. Okay. If I get up to the number 99 and I add 1 to 99, now I increment to the hundreds column. Okay? So we're familiar, ones, tens, hundreds. Cool? Okay. So those are going to be my basic units of measure. This could be pounds, ounces, volts, amps, miles, whatever. Now, if I go here to my thousands column, 1,000 column, basically what I'm doing now is this is times 10 to the third. Times 10 to the third. Everything in here will be times 10 to the third. This could be 1 times 10 to the third, 22 times 10 to the third, 943 times 10 to the third. Make sense? The reason that I'm so infatuated with having you put it in engineering notation is by 10 to the third, we're going to call this value here in the metric system what? What's thousands in metric? Kilo. Very good. Kilo. So what we're going to do is we're going to call this, small letter K, kilo. So instead of saying 1,000, I'll say 1K. Instead of saying 943,000, I'll say 943 kilo. Kilo pounds, kilo ounces, kilo miles, kilo volts, kilo ohms. Make sense? Kilo miles. There's a new one for you.
So resistors expressed in K, meg, kilo, or that's all basically, it's scientific, or it's engineering notation.
Well, metrics, it's in metrics, but if you put it into engineering groups of 3, then it's going to fit directly into those prefixes, those metric prefixes. So 3 more places past the decimal point. 1, 2, 3. This is times 10 to the 6th. We're going to call this mega. Mega. And in actuality, it's like millions, right? 1 million, 10 millions, 100 millions. Mega. Ten to the 9th. What's that? Giga. Very good. Capital letter G. Giga. When I first got into this industry, I'm dating myself. I don't know why I say that. I make myself feel old. This is as far like as we had gone in the electronics industry. General Electronics. Giga. Wow. And I'll be honest with you. Where I used to work in electronic intelligence, the only people that could afford to play up here in giga values were superpowers. It was either us or the Soviets, and we knew what we had, so if I detected something that was in gigahertz, it had to be the Soviets. Okay? Now, giga, commonplace. After school today, you could probably stop at Fred Meyer, pick up a laptop computer that's got a, 80 gigabyte drive in it for $49. That's actually too much money. $49 you could get a times 10 to the 12th, tera. Tara also happens to be a barista down in Federal Way that's kind of got it going on, if you know what I mean. I don't even know what I mean. I don't even know what that is. Tara. When I first started teaching here 20 years ago at Lake Washington Technical College, boy, I can't even remember. I think I might have had like an 80 meg hard drive or something. I remember getting super jazzed by getting the Sunday Seattle Times, and I saw an ad in the paper that I could get like a 250 megabyte hard drive for less than $1 per megabyte. And I'm like, you gotta be kidding me. I could get less than $1 per megabyte of storage. I'm gonna go out and get one of those. So I went out and paid my 250 bucks or whatever. Now you're getting a terabyte hard drive for $49. Now they have 2 terabyte hard drives they could get for $99. So this is, have I made my point about the numbers we're going to work with in high-tech industry? I mean, the numbers are extreme. They're extreme. So again, if you use engineering notation and put it into groups of 3, and most of you on your calculators have a mode that you could put it into engineering notation. So ultimately, the answer is going to be given to you in either times 10 to the 3rd, 10 to the 6th, 10 to the 9th, 10 to the 12th. If you don't know how to do that, you might want to look at your owner's manual. If you already threw your owner's manual away, do a Google search on your model, and it'll come up with a PDF of it. Okay? You want to make sure you know how to access those modes in your calculator, because again, we're going to be using some extreme numbers. But you know what? I'm not done. I've yet to begin. We're about halfway done. We're also going to be dealing with numbers that are smaller than 1. So when I go back 1, 2, 3 places, anybody know what we call these? Times 10 to the negative 3rd, 3 places to the right of the decimal place? Milli. And actually, if any of you come from a machining background or whatever, like thousandths of an inch, this would be a tenth of an inch, right? This would be hundredths of an inch. This would be thousandths of an inch. And you use the term mil, right? How thick is that plastic? 3 mil. 3 milli. Okay? So we're going to call this small letter m for milli. M-I-L-L-I, milli. 3 more places past the decimal point gives me times 10 to the negative 6th. Anybody know what we call this? Micro. Very good. Micro. Micro is kind of weird too. It's a Greek symbol. Kind of looks like this. It's kind of like a backwards U. It's actually the Greek symbol called mu. Mu.
Dirty jobs too.
Dirty jobs?
Micro.
Really?
Micro.
He does that? Micro. For our friends at home, yeah, micro. He actually participated in a fundraiser here in the fall with Lake Washington Technical College via satellite. Actually, the producer from that show, Dirty Jobs, was here, and as a fundraiser for our college foundation. But Micro was live via satellite, speaking directly with all those that went to breakfast here at Lake Washington Technical College. I slept in that morning. I was hoping they were going to TiVo the event so I could watch it at my leisure, but nobody TiVo'd it. 3 more places past the decimal point times 10 to the negative 9th.
Nano.
Yep, nano, very good. Small letter n. Small letter n, nano. Any of you have heard about nanotechnology? This is kind of like where nanotechnology is playing around with now. 3 more places past the decimal point times 10 to the negative 12th. Pico, small letter P, pico. Suffice to say, I could go further. There's a couple places past this, but it's beyond the scope of what we're talking about right now. But as students at Lake Washington Technical College, you on a regular basis are going to be dealing with numbers times 10 to the negative 12th to times 10 to the positive 12th, sometimes in the same problem. So like I said earlier, even if you're Bill Gates' accountant, even if you're the IRS itself, anybody here not filed their taxes yet? 2 of us? 3? Be honest. 4? It's actually funny. I was with friends on Saturday. We stopped at Starbucks for a cup of coffee, and my friend saw this woman that she thought she recognized, that she knew, and you can't make this stuff up. It's like, she's like, you look like a good friend of mine, blah blah blah. And do you work for Quest? No, I don't work for Quest. Well, I work for the IRS. Really? Excuse me, ma'am, but you look lovely today. Can I buy you a pastry to go take a cup of coffee? Hey, you don't want to tick those people off. It's who finally brought down Al Capone, wasn't it? Right? The IRS. Anyway, we're going to be dealing with numbers like this, so we have to make sure we get it right. So in most of your calculators, you'll have a key EE, and you could enter that. Whatever you do, do not enter it as it appears here on the, don't go 3, hit the times key, 10 to the third power. You're actually going to end up a decimal place off with that. You have to enter it, the EE key, exponential notation. Any questions on that? All right. There's no harm in using your imagination when you're dealing with an electrical system in equating it to a fluid system. Because let's be brutally honest, you can't see electricity coursing through wires. You can't see it. Our 5 senses are very, very limited. So sometimes analogies really, really help us out. So for those of you that understand fluid systems, it all rolls downhill and, pressure and pumps and that kind of stuff, you could use the same analogies to figure out what's taking place inside an electrical circuit. One of the things that I do, because I just love Seattle, is I'll use the Seattle freeway system to sometimes explain the behavior of current in a circuit. I-5, 405, 520, and we'll use those as analogies of how current behaves, how traffic behaves on a Friday before a 3-day holiday weekend, and it's sunny out, and raining in the convergence zone. And we'll use those analogies to kind of figure out what's taking place in a circuit. So this analogy shows us the pump. This would act like our voltage source, right? It's sucking and then discharging, right? So this is our source of electrons, and this is where it's drawing the electrons through. So the pump. The current flows through the plumbing. The electrons flow through the circuit. The only thing that I would have done differently if I drew this illustration, I can't take credit for this, I simply pulled it out of the text, is the load. This would have been nice if they had like a water wheel right here. So as the water runs by, it turns the wheel, because that's what a load does. A load converts one form of energy to another form of energy. An electrical load converts electric energy into light energy, or electric energy into motion, or some other form. Does that make sense? So you can use this if you care to. Since this chapter is talking about current, typically in the study of electronics, not electrical, but electronics, we're typically only going to be using values associated with milli, times 10 to the negative third, milliamps, which, don't be fooled, milliamps could kill you. There's enough, even though it's thousandths of an amp, it's still enough to kill you. More than enough to kill you. And also we're going to be dealing with microamps. Typically, as a student here in the electronics program, Lake Washington Technical College. For those of you that go into the electrical trades at all, you're going to be dealing with amps. And lots of them. We had a student that just got hired by Bonneville Power Administration, BPA. He's going to be working substations. I don't even know how many amps you're dealing with at a substation. What makes a substation a substation? Lots of amps, I would imagine. Okay? I never had an interest in working with that many amps. Since milliamps could kill you, why would I want to work with more than enough to kill me? In summary, we talked about the laws of electrostatic charges. The first law is that like charges oppose each other. The second law is unlike charges attract each other. A coulomb is 6.24 times 10 to the 18th electrons. Electric current is the flow, not the drift, the flow of electrons in a specified direction. Measured in amps, conceived by the dude by the name of Andre Marie Ampere. And Andre Marie Ampere stated that 1 amp is equal to 1 coulomb per second. That's the relationship between current, electrical charge, and time formula. We talked about holes moving. Holes move in the opposite direction of electrons. Electrons travel negative to positive, holes travel positive to negative. We talked about scientific notation. Negative exponents, specifically milli, micro, nano, and pico. And we talked about positive exponents, specifically kilo, mega, giga, and tera. And tera also happens to be a in. That's kind of got it. Outstanding. If you know what I mean. I don't even know what I mean. We're going to talk about milli prefix. Typically, these are the values of current that we'll see in an electronic circuit. And also micro, times 10 to the negative 6. These are also values of current we'll typically see inside an electronic circuit. Make sense? Anybody have any questions on anything that we covered in Chapter 2? Chapter 2. All right, let's go ahead and take about a 15-minute break, and at 6:45, we'll go ahead and kick things off again.